Alright, so we saw now we're going to take a measurement every second. So we generate a signal and we're measuring it every second. So there's now a few concepts that we have to discuss again. Let's clean this mess up. File new. So there's two kind of important things when you start digitizing something, when you start recording something digitally. The first thing, if you look at this value, we're getting a value, just put my brush on, getting a value like this. It goes from 0 to 40, maybe 40 degrees is there. Yeah, it goes 20 degrees back to 0. So 20 degrees there. So it means it's stepping up, stepping down. So this is kind of what's happening in nature, in the factory, in real life. It's changing its temperature. If we measure the stuff and we measure it every second, if this is 2 Hertz, remember we said a full cycle, whoops, sorry. We said a full cycle will be 2 Hertz from the factory, 2 Hertz. Means there's a change every 2 seconds. If we only measure a value every second, we're going to see what values. Let me change the color there. Every second, it means I might measure the 0. So I'm looking at the multimeter. I close my eyes for 1 second. I might measure again. I see 0 again. So it might look for me that the machine is not working because I'm not taking measurements fast enough. Does this make sense? Remember, the computer only has a certain amount of speed, so I slowed it down a lot to say 1 second. But if you're a human taking it with a book and a multimeter, these values, you could see maybe if you looked up and down, 1 second would have passed and you only measure certain points. And you would miss some of these inputs. And in control, this is important not to miss inputs. This is now kind of called the Nyquist rate. You can Google this as well, Nyquist rate, Nyquist frequency. So what the Nyquist frequency says, you have to look at your highest frequency and you have to sample at least double that, double the speed of your highest frequency. Now the thing is here, this is not our highest frequency. If we look at our noisy signal, remember the noisy signal looks something like this, which was a combination, if you can start getting the feel for it, of a high frequency and a low frequency. So sometimes when you do signal analysis, you'll try to measure as many points as possible so that you can pick up high frequencies as well. So your highest frequency is the issue. So that's why, remember I said 200, make it 200 Hertz. I'm going to generate a noisy signal. I'm going to explain it now at 50 Hertz. So let's say we analyze the signal. We saw that we've got our low frequency, which is this one, a 2 Hertz frequency. And we got a high frequency noise. That one was a 50 Hertz. I'm going to show you now how we're going to analyze this. First we have to generate it. Why do I choose 50 Hertz? Most countries generated a 50 Hertz signal. So your power source from the plugs from the mains are normally 50 Hertz. And that 50 Hertz has got a nasty habit of sneaking into your signals. You can sometimes pick it up, especially if you have long cables and so on. You'll pick up that 50 Hertz. So we're going to get a signal like this. We assume, I'm telling you now that this signal consists of the signal I want, the 2 Hertz signal, plus a 50 Hertz noisy signal. Again, later we might analyze it, find different noise levels and so on. Depends on your application. But for this example, we've got 2 signals, the actual one and the 50 Hertz, which is the noise one. I hope you understand the explanation there. So, sample frequency, or sample rate, Nyquist rate, sample frequency. Let's just start here with a new file. So, new file. So sample frequency, it means in nature we get something like this. We want to measure it, but we only measure certain points at a sample frequency. All digital circuits sampling work like this. Your computer says, what's the value now? What's the value now? What's the value now? So it takes a sample there, a sample there, a sample there, a sample there. So the only thing the PC sees, the computer see, or your machine see is discrete points. Now your brain is kind of an amazing thing. You can already see Your brain already sees a sine wave there. The PC doesn't see it. Computer doesn't see a sine wave there. It will make for you. So whenever you see on a computer a sine wave looking like that, it actually draws the picture for you. There is no value there. There is no value there. The computer draws the process for you because it knows, or the programmer knows, humans doesn't like looking at points. It likes looking at lines. So it will just draw the line there, but in memory on the PC there's no value there in between. Just something to remember. So again, if you sample, the Nyquist rate says you must sample at least double your highest frequency. So if this is your frequency and you sample, if that's your frequency and you sample at least double, means you're going to sample there, 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 and so on. So your output actually looks, your PC it looks like almost a type of square, sawtooth, triangle wave. So the least amount of samples that you can take, measurements that you can take, is at least double. I like 4 times. 4 times is much better, because if you have 4 values, you can more clearer see that sine wave. You can see with 4 values, you can see better. Where with double the highest frequency, it really just looks like a triangle. So Nyquist rate, go into it. Nyquist rate, double the highest frequency. So remember I said we're going to generate 2 sine waves. So let's just make that 2 sine waves here. We're going to make the information one, the one that's making our 2 Hertz value going from 0 to 40. We're going to make at a sample frequency of 200. You can make it much higher this, it doesn't matter now, but I'm going to kind of stay 200 with one sample, one value. Let's add another one. Right click, express, input, simulated signal. Frequency 50 Hertz. I'm making the noise now, the noisy one. 50 Hertz signal. Amplitude, I'm going to keep it small. Remember, noise is not that big. Remember, the other one was 20. I'm going to make this 5 samples per second. It must be the same as the other one. 200 samples. I've got 1 sample that's running. It says simulate acquisition time, and we can do that. We just change the other one to simulate acquisition time as well. So what do we have now? We've got one that's making 2 Hertz, one that's making 50 Hertz, and I'm going to add them together. Take this one, add it to this one. Just going to delete that wire there. So now I've got the noisy signal. Remember in the beginning I said if you add 2 frequencies together, it's going to make you the noisy one. Still difficult to see because we don't have a waveform yet. So let's change our frequency. Our sample frequency is way too low. It's 1 Hertz at the moment. So what is our highest frequency? Our highest frequency is the noise one at the moment. We just clean this up. So what did we make? We make 2 sine waves. We generated 2 sine waves to simulate our operation. A big one that goes from 0 to 40, and a small one goes from minus 2.5 to 2.5, because we said it must be 5, the amplitude is 5. Just delete this again. So small frequency, we're going to plus them together and it's going to give us something like this. We're going to see it now on the software. We still have to write a program to show you the waveform, but for now, this is what's happening. It's slowly going up every 2 seconds. It's going to do a full cycle. This is our highest frequency is 50 Hertz, and the Nyquist rate said double our highest frequency, which is 100 Hertz. So we have to measure at least 100 Hertz. 1 over T is equal to F. So it means 100 times per second. If you put it in that formula, you see I have to take measurements 100 samples times per second to actually see that waveform. Now, I'm just going to make that more. I'm making it 200 so that we get a better picture, a better resolution picture. If that makes sense, 100 will work, but 200 will work better. 1000 will work even better. The problem is the faster you make your PC, unnecessarily, the faster you make your software, the more processing power you need. And some processors won't be able to do all the maths that you want. So try and make it as low but also as high as possible for your processor and your system. So 200 Hz, so if f equals 1 over t, we make t subject to the formula. This is f, we calculate our t, we'll see it's 5 nanoseconds for 200. Let's just see here. 1 divided by 200 will give us 5 milliseconds. So instead of once every second, we're going to measure at 200 Hz, so every 5 milliseconds. So if we see now, we can see there it's jumping up and down. You can see the noise, the signal is quite noisy on that system. Just going to stop it here. Let's take out that waveform. How do I take it out? I make its amplitude 0. You see, so I'm just switching it off. So just a clean noise. You can see that it's going nicely up and down. That needle jump is just because the refresh screen, I suspect, of the video is not high enough. See, it's a clean signal. The moment I put the noise in, it's going to jump around. Typically what you'll measure, hopefully you've seen this in systems before, you know, a needle that jumps around, values that jump around. Let me just slow it down just to show again. Let's make this 0.5 just to make it visually more clearer. Can you see that noise? See that needle is jumping around a lot. If I make this amplitude 0, removing the noise for now. Remember, we add the noise to the signal. What do we see there? This looks around about what you're supposed to get, but for some reason we have noise there. 1. You can see there, jumping around. Values jumping around. Alright, so this is what we're doing now. We're measuring the values. We're taking one measurement at 200 Hz or every 5 milliseconds. If we want to see it on a waveform, we can put a graph here. We want to see it on a graph. We have to record values. Now remember, if you did this with a little book or in Excel, it means you have to add a few values. You have to measure the values, put it in an Excel sheet, and then take that 10 values or 1,000 values, then plot the 1,000. In this case, can you see there's 100 values? You want to plot the 100 values, so value 0, value 1, value 2, value 3. The moment you start doing this, you can't really control anymore, because you have to wait for that 100 samples to be done, that 100 measurements to be able to display it. But we want to see what's going on. So this is typically a control circuit, one sample at a time. Is it too high, is it too low, switch it on, switch it off, and so on. But if you want to see something, we have to put a graph there, and we have to put a for loop there. So for, a little bit of programming here. For, I'm going to put it in here. I'm going to put that timing in here. I'm going to explain how it's happening. And on this one, create constant for 100 values. So this for loop is going to take 100 values. It's do this 100 times, measure 100 values, and then display it on a graph. Then the while loop is say start again. After this for loop is done, after 100 times recording, 100 values were recorded, it's going to start at 0 again. Taking value 0, what was the value? Value 2, what was the value? And it waits 5 milliseconds before it takes this recording. So let's quickly see here. Can you see there? It's now demonstrating. So it shows you 100 values, 100 values, 100 values. It looks like it's real time, but it's really slow. It actually needs to wait for the value. And then that is the last, that's the value that's actually happening inside there. If I put it there on the outside, there will be only, it will be much slower. If I put it on the outside, I wire it in there, and I'm going to show you just the last value of the while loop. Just change this to last. Path value. So this one index the values, this one makes an array of values. Maybe I must